Earlier, I used the idea of thinking of a set as a circle to graphically illustrate some of these things. I want to formalize this more here. That object actually has a name. It's called a Venn diagram. And in a Venn diagram, the rectangle around the circles represents the universal set. The interior of each circle represents the elements of that set, and we've done this before, so this is sort of just formalizing what we've already been doing. So the interior set A, the interior set B. They represent the elements of those respective sets. If you look at these two different colors I've used for the interiors of the sets, the blended region, the region that has a blended color, this region here, represents the intersection. A intersect B, the intersection of those two sets. This is a Venn diagram. What do you do with it? Let's just do some things that get you used to the concept. Suppose I take a Venn diagram with two sets A and B, and I represent the number of elements in various regions on this Venn diagram by R sub 1, R sub 2, R sub 3, and R sub 4. They stand for numbers. R sub 1 might be 7, or R sub 3 might be 18, whatever. Those are just placeholders for actual numbers. Looking at that, how many elements are in set A? Well, that's pretty easy. R sub 2 and R sub 3 are both in A. So to find out how many elements is in the set A, you simply add up R2 and R3. R sub 2 plus R sub 3, whatever those two numbers happen to be, would add together to give you the number of elements in set A. I could also ask how many elements are in the union of A and B. But remember, the union of two sets is just everything in either or both sets. So the union of A and B will simply be what's in A, what's in B, or what's in both. So that would be R sub 2 plus R sub 3 plus R sub 4. Okay, how about the number of elements in the intersection of A and B? Remember, the intersection is simply the overlapping part. So that would obviously be just R sub 3. What about the complement of A? How many elements would be in the complement of A? Remember what the complement of A is. It's everything that's not inside of A. So I've shaded every part of the Venn diagram that's not inside of A. Anything that gets shaded is in the complement. So it's easy to see now that the complement, the number of elements in the complement would just be the number represented by R sub 1 plus the number represented by R sub 4. So R sub 1 plus R sub 4 is the number of elements in A complement. What about the number of elements in B minus A? Now remember, we talked about the difference of two sets. The region represented by B minus A is the set B with anything that was in A taken out. So the set B itself is the region I've shaded in blue here. But when you say minus A, you have to take out anything that was also in A, and it's obvious that this R sub 3 has to come out because it's inside of A. So when you're done, the only thing left in B that wasn't in A is R sub 4. So the number of elements in B minus A is R sub 4. You need to play around with this yourself, not just watch it being done by someone else. It's also true that you can use Venn diagrams when you're dealing with three sets. In fact, that may be when it's most useful. For example, suppose I have a universal set with three sets, and I'm calling them B, C, and H. And each region of that Venn diagram has the number of elements indicated here. Let's play around with that. One thing I could ask is, how many elements are there in the intersection of B and C? Well, if you look through here, B and C intersect there. That's the intersection. That's where they overlap. So obviously, that would be 3 plus 4 or 7. So there are 7 elements in the intersection of B and C. What's the number of elements in B intersect C intersect H? Now this one you may have to think about a little bit, and what I would suggest is thinking about the overlap of 2 circles becomes now 3 circles. So what you're saying is, what are the elements that are in all 3? They're in B, and they're in C, and they're in H. And obviously, this region here is the only region that's a part of B, and a part of C, and a part of H. So the number of elements in B intersect C intersect H would be 4. Now this one you really have to think about. It says how many elements are in B complement intersect C complement intersect H complement. I would highly suggest you sort of word this out, say it in words. Think about it this way. This is the region that is not inside of B, intersections like and it's not inside of C, and it's not inside of H. So we're looking for the region that are not inside of any of those 3 circles. When you say it that way, then it becomes pretty clear that these 12 elements out here are the only ones that are not inside of B, and not inside of C, and not inside of H. So you're looking for the number of elements in the intersection of the complement of all 3 sets. It'll always be the area or the region that's not in any of the circles. These are how Venn diagrams, or examples of how Venn diagrams can be useful. So the number of elements in the intersection of B complement, C complement, H complement is 12. Let's look at another example. I did a survey, say, of 95 consumers, and here's what I found out. Of those 95 consumers, 60 of them had a credit card. I counted my survey results and counted to 60. Then I looked at people who had a debit card, did my count, and there were 40 people who had a debit card. Finally, I wanted to see how many had both, so I went back and looked, and it turned out that 15 people had both a credit card and a debit card. Here's the question. How many people surveyed had neither? They didn't have a credit card, and they didn't have a debit card. They didn't have either one, either credit or debit card. That's what I want to know. A Venn diagram is perfect for answering a question like this. I only have 2 sets. One set I'll call C, are the consumers who have a credit card. The circle I'll call D are the consumers that had a debit card. And I'm allowing for overlap. Those will be the consumers who had both. So after I draw my Venn diagram, I want to start on the innermost region. If I can possibly know that number, that's where I want to start. I always look to the center if you can. And I do know that. My survey results came out that 15 people had both, so I put that in. And then you sort of work your way out. I also know that 60 people had a credit card. Now remember, that means that there are 60 people inside of that circle C. So your first inclination is to put 60 right here where this question mark is, but that's not correct, because that would mean 75 people had a credit card, because those 15 people that you've already documented are part of that 60. It didn't say 60 people had only a credit card. it said 60 people had a credit card. Now the word only does pop up occasionally, and we're going to do an example of that in a minute. But right now it just said 60 people had a credit card. That means in this entire circle called C, there have to be 60. So what I have to do is a little subtraction. I've got to say, well, something plus 15 has to add to 60. And of course, that would be 45. So the 45 goes there, not 60. But 45 plus 15 is equal to 60. If you add these two numbers, you get the 60 people in the circle C. So be careful. The other thing I know is that 40 people had a debit card. Again, the first inclination is to put 40 where this question mark is. But that's not what it says. It says 40 people had a debit card. It did not say 40 people have only a debit card. The word only would be an indicator when you read that to actually put the 40 where the question mark is, because those are the people who have only a debit card. But that is not what it said. It says 40 people are inside of circle D because they have a debit card. So I've got to again do a little subtraction. What plus 15 will give me 40? And of course that turns out to be 25. So I put 25 in where the question mark was, and I notice again that 15 plus 25 does give me 40. It's not difficult, but you have to be careful. And lastly, I want to find out how many people don't have either one. So what I need to do is figure out how many have one or the other. So I want to add 45, 15, and 25, and that's really just the number of elements in the union of those two sets. So the number of elements in the union of those two sets is 45 plus 15 plus 25. In other words, I'm just adding these three numbers. So there are 85 consumers that have either a credit card, debit card, or both. But remember, there were 95 consumers in all. So of the 85 people that are in one circle or the other, there are 10 people unaccounted for. That means that you have to subtract 85 from 95 to figure out how many people have neither one. So it turns out that 10 consumers don't have either a credit card or a debit card. And putting it back, I had eliminated the subregions of those circles, but putting it back, that's what you finally get. There are 45 consumers that have only a credit card. There are 25 consumers that have only a debit card. There are 15 consumers that have both a credit card and a debit card, and there are 10 consumers that have neither. And the question was, how many people had neither? That was the actual question we were being asked. So there were 10. 10 people had neither a credit card nor a debit card. Venn diagrams are perfect for problems like this. Let's bump it up a little now and do a problem where you have three circles. This problem says you have 30 members in a 9th grade class. Some of them are in band, some are in choir, some are in history. If you look through there, there are the only three in there, so you want a three-circle problem. You've got to draw a Venn diagram. I sort of overlooked what the question is because at this point I don't really care what the question is. The actual question is how many 9th graders are in one or more of these groups. But at this point I really don't even care about what the question is. I just want to get my Venn diagram drawn. I'll have a band circle, that's the B. I'll have a choir circle, that's the C. And I'll have a history circle, that's the H. Then I want to start, again, as with the two-circle problems, I want to start with the innermost region if I possibly can. Those are the students that are in all three. They're in band and in choir and in history. And as the problem tells us, there are two of those students. So I put 2 in that overlapping region for all three circles. So you want to start on the innermost region if you possibly can. If you don't know that, you'll have to put an X in for it or something. But if you do, that's what you want in there. And keep moving. Go to these other interior regions. You sort of start in the middle and you wind your way out. So, for instance, I might want to look at the region I have shaded in green here. I call it a football-shaped region. It's that region right there. Those are the people, that's where B and C circles overlap. So those are the people that are in band and choir. But remember, and I referred to this in the previous problem, I said that word only was something you should watch out for because in the other problem it wasn't there, but in this particular part of this problem it is there. It says that there is one person in band and choir only. That means they are not in history. So if I look at the people that are in, going back, if I'm looking at the people that are in band and choir, if that word only weren't there, then that whole green area would have to be 1. But it says only. The only eliminates the possibility that they could also be taking history, which takes them out of that history circle. So when you see the word only, that's a clue that the number you're dealing with is going to be in a subregion of the region you get by ignoring the word only, if that makes sense. So in this case, your intuition might tell you, after you've gotten used to working with the other problems, that you have to add those two numbers to get 1. But in fact, when you have only, it's going to go straight into that region. These are the students that take band and choir, but that's all they take. They don't lie in this region because if they did, they'd also be taking history. So think about that and be really careful. That word only is something you need to watch out for as you're reading these problems. So in any case, there's only one person in that region taking band and choir, but not history. And we wind our way out. Now how about this region? This orange region, this football-shaped region here, says there are 3 people in choir and history. But it doesn't say only this time. So you just really have to think. It says there are 3 in choir and history. So that entire orange region has to add up to 3. It doesn't say choir and history only. If it did, you'd have to go back to the analysis we used for the previous one where it did say only. Whenever the word only is not there, you're going to be adding 2 things. So this is more like the problem we did with the 2 circles where you've got to think about what adds to give you 3. You already have a 2 inside of that orange region. You want the numbers to add up to 3, and obviously that would be a 1. And 2 plus 1 add to 3. And you keep going. Now we're looking at the people who are in band and history. Well, that's the region where the B circle overlaps the H circle. That's the region I have shaded in purple here. Again, it says 4 people are in band and history. It doesn't say 4 are in band and history only. If it doesn't say only, you're going to be doing some addition. So what you really want is every number in the purple region has to add up to 4. You already have a 2 in there, so obviously the other number is 2. And you've got that. So we're winding our way out. We started with the innermost region, and then we've gotten the other 3 regions that are closest to that region. Now we're going to the outer regions. So maybe we're going to take the history circle. If you look at this, it says 15 people are in history. That means that inside of that circle that's labeled H, there have to be numbers that add up to 15. It doesn't say taking history only. If it said history only, the 15 would go where the question mark is. Those are the people that are taking history only, but it doesn't say only. It says there are 15 inside the history circle. So this is an addition problem. You want to take each of the numbers inside of the history circle and add them together and make sure it comes out to 15. Well, that's an arithmetic and a simple algebra problem. 2 plus 2 plus 1 is 5, and if you subtract 5 from both sides, you'll find out that the question mark is equal to 10. So you have to put a 10 in that region. Those are the people that are taking history only. And then you repeat that for the other circles. So maybe you go now to the choir circle. The choir circle has to come up with 9 because it says 9 are in choir. Not that 9 are in choir only, but there are 9 people inside of the choir circle. So again, it's an addition problem. You have to add up all of these numbers and set them equal to 9. And of course, 1 plus 2 plus 1 is 4, and if you subtract 4 from both sides, you'll end up with a 5. So there are 5 people who are taking choir only. But when you add up everybody in the choir circle, you get 9, which is what it says. And finally, you go to the band circle. There are 9 in that as well. So everything inside of the band circle, this plus this plus this plus this, has to come out to be 9. So 2 plus 2 plus 1 is 5. Subtract 5 from both sides, and you'll find out that there are 4 who are in band only. But a total of 9 who are in band. Now the only thing we don't have are the number of students who aren't in any of those circles, that aren't in band, aren't in choir, and aren't taking history. So what I can do is just add up everybody that I've already accounted for. If I add 4 and 1 and 5 and 2 and 2 and 1 and 10, I come up with 25. But notice there are 30 students in that class. So that means that the other 5 of them must be outside of all 3 of those circles. So those 5 students aren't in band, aren't in choir, they're also not in history. At this point, I've completed my Venn diagram. I've labeled every section, every region of that Venn diagram. So now at this point, I am ready to go back and look at the original question. Now the original question says how many of those 9th graders are in one or more of these groups. Well, that's easy, because what I really know is that there are only 5 that aren't in one or more. Well, if you have 30 and 5 aren't in any of those groups, that means that if you take 30 minus 5, those other 25 students are in one or more of these groups. In other words, they're inside of one or more of the circles. Only of the 30 students, the only ones that aren't in any circle at all are those 5. So 25 are. So the answer to the question, there are 25 9th graders that are in one or more of these groups. So keep practicing with these. Venn diagrams are a very powerful way of dealing with problems like this.